Hello, this is Ms. Nichols, and the topic of this video is resistor-capacitor circuits, sometimes called RC circuits. And the essential question is, how do capacitors act in a circuit with a battery and a resistor? Okay, let's do a quick capacitor review. In the last unit on electrostatics, we used capacitors primarily for the way that they generate uniform electric fields in the space between the plates. But this unit, we're concerned more with the amount of energy storage they provide, because that's what we need in a circuit as a source of energy. So we can use them in place of a battery in a circuit. Here is a schematic picture of a capacitor. You'll remember that it's got two big parallel plates, and if you connect those to a voltage source or a battery, electrons get pushed on and off of those plates. And that's basically what a capacitor does. And we've got the schematic symbol next to it, which is two parallel lines that are equal length with each other. A couple equations that are a review but useful in this unit as well. That first equation allows you to calculate the amount of electrical potential energy stored in that capacitor based on either knowing the number of charges on the plates and the voltage, or the capacitance of the capacitor and the voltage. And the second equation was our, how do we build a good capacitor? So capacitance has a linear relationship with the area of the plates. So the bigger the plates are, the better the capacitor is, and an inverse relationship with the distance between them. So those are both going to be really relevant in this unit as well. A couple pros to putting capacitors in circuits instead of batteries, or in addition to batteries as your power source. The main one is that capacitors do not have a flow rate of current that is limited by the rate of a chemical reaction. So in a battery, because it's continuously pumping the same electrons through and through and through, in a perfect battery, you should be able to just have an inverse relationship with the resistance. But in a real battery, the chemical reactions have to occur for the electrons to move from one side to the other, and that actually slows it down. So unlike that, in capacitors, all the electrons are already on the plate. They're already ready. They don't need to get pumped from one side to the other. So we can actually dump all of those electrons really, really quickly. So for some very high current applications, capacitors are great, like flash bulbs on cameras, etc. One of the cons, of course, for capacitors is that the total power provided by the capacitor is limited by how many charges you store up on the plate. So we get a lot of current, but we only get it for a very short amount of time. And then the current actually dies down as the voltage dies down as well. So they don't provide the constant current and flow rate that batteries do. It's more of a little spike situation. So what happens if we connect multiple capacitors together in series and in parallel? Well, it's all going to boil down to this fundamental definition of capacitance, just like attaching resistors in series and parallel boil down to the fundamental definition of resistivity. But it's all kind of flipped, as you'll see in just a minute. The total capacitance of two capacitors in series is actually less than the individual capacitance. So this is a less good capacitor to attach them in series. And the reason is because we've basically added together the distance between those capacitors. We're separating the sides of the battery by a larger distance because there are two gaps instead of just one. The equation to calculate capacitance in series is 1 over the total capacitance in series equals 1 over C1 plus 1 over C2 plus 1 over C3, etc. So if you have a bunch of capacitors stacked up in series, you add the reciprocals, and then you take the reciprocal of the solution to get the total capacitance in series. One note about this is really important. The Kirchhoff's laws work for capacitors as well. So both the junction law and the loop law work for capacitors. So if you think about the junction law, it says the current has to be the same everywhere in a wire. So if I've got two capacitors connected in series, the current on that top part of the wire is the same as the current in the middle. It's got to be the same as the current on the bottom. Even though the electrons aren't technically going through the gaps, the junction rule still applies. Where this comes into play is when we think about the charges stored on the plates. Because the current has to be the same, and because we can't create or destroy any electrons in our circuit, every plate of those four shown must have the same amount of net charge on it if we want to follow those rules. So if we have a +2 Coulomb charge on the top plate, we're going to have corresponding -2 on the bottom plate, and then again we're going to have a +2 on the top of that bottom capacitor, and a -2 on the bottom of that plate as well. And this is regardless of the values of the capacitance. So these are kind of shown as equal capacitors, but even if C2 was a much higher capacitance capacitor, we still have the same Q on both of those plates because of the junction rule. And a further implication of this is that means that when two capacitors are in series, we are going to have a bigger voltage drop across these smaller capacitors. There's an inverse relationship. This is shown in that equation that we got last unit. Delta V is equal to the Q on a plate divided by the capacitance. And so basically you can see there's an inverse relationship. If Q is constant, if both capacitors have the same Q, then the smaller capacitor has a bigger voltage drop, and the bigger capacitor has a smaller voltage drop. Here is an image showing this. I don't love this image because they've got weird units on there. I've got nanofarads and microfarads. A microfarad is actually bigger than a nanofarad, so that bottom capacitor C2 is a larger capacitor, and you can see that there is less voltage stored in the larger capacitor when we are connecting them in series, which is consistent with that relationship. What about connecting two capacitors in parallel? Well, connecting two capacitors in parallel provides a larger amount of total capacitance than the individual capacitors, because what you've essentially done is you've increased the plate size. You've provided more space for those electrons to spread out. And so the equation for calculating capacitance in parallel is just add up all the capacitors individually. C1 plus C2 plus C3 is going to give you your total capacitance in parallel. Of course, you probably noticed at this point, these two equations are just exactly the opposite of the resistance equations, and that basically has to do with how those devices are built and the functionality of those devices, but it's kind of a cool little parallel as long as you can remember that they're opposite from each other. Going a little deeper into our parallel capacitors, the voltage drop has to be the same across both of those capacitors connected in parallel due to the loop law, of course, because electrons are going to go one route or the other, and we have to have the same amount of energy regardless of which route we take. And so that means, of course, by that equation that we've been talking about on the last slide, if V is the same for both, then we're going to have a linear relationship between Q, or the charge stored on the plate, and the capacitance. So in the diagram shown, let's pretend C2 is a bigger capacitor, so either the plates are bigger or they're closer. That capacitor is going to store more charge on its plate than the smaller capacitor is for the same given voltage. So realize that relationship works this way when you're connecting capacitors in parallel. So when you first connect a capacitor to a battery, electrons are gonna flow very rapidly to the surface of that capacitor, but the fuller it gets, the slower it goes. So there's actually kind of a logarithmic capacitor charging function that depends on several variables about the capacitor. We're not going to go into the details of this function because it's kind of beyond the math scope of this class. So in this class, we are only concerned with two kind of instants in time when we're talking about the capacitor charging. And the first moment that we care about is called immediately. Immediately is in that very, very first tiny fraction of a second when you first connected the capacitor. And in that immediately time frame, the capacitor basically acts like a closed switch, in other words, a plain wire in the circuit. And what I mean by this is that current flows onto the capacitor on one side, and it flows off of the other side of the capacitor, even though we're not actually going through the gate, the gap between them. We could still visualize it as going basically through that gap. Just as if that capacitor was just a plain old wire. It has no resistance, it has nothing, it has no effect on the rest of the circuit in that immediate time frame. The circuit just acts as if the capacitor isn't even there, and if you're asked to find what's going on in other components in the circuit, you can basically use Ohm's law to figure out what's going on. The other time interval that you're interested in is called, quote unquote, a long time after, okay? And now we've reached this steady state, we're basically all charged up moment in time for the capacitor. And once we've reached that state, it's kind of the opposite, because the plates of the capacitor are totally full, and that means I can't accept any more electrons from one end, and I can't send any other electrons off the other end. That capacitor functionally acts like an open switch in the circuit, or a broken wire that doesn't allow any electrons to go through. During this time interval, no current is flowing through the wires connected to the capacitor, either on or off, and that's going to affect the devices in the circuit as well. So you would want to imagine that circuit as having a broken wire there. You could still use Ohm's law for the circuit if there were still other complete pathways to get back to the battery, but no current will go through the wires that are connected to the capacitor. So let's see how this works in a couple sample circuits with resistors and capacitors in them. This is just a series circuit that has one single resistor and one single capacitor. In that immediate time frame, as soon as you first connect this circuit, current is going to flow into that circuit all the way through the circuit as that capacitor is charging. So we're flowing onto the top plate and off of the bottom plate, and the circuit itself is going to obey Ohm's law. So for the R total for the circuit, it's just going to be the resistance of that resistor. And during this time interval, that resistor is going to be dissipating power. It's going to be, currents flowing through it, energy's dropped across it. Therefore, we're going to have power, and if it's a light bulb, for example, it's going to be lighting up. Now, once we've reached the a long time later time interval, that capacitor is now fully charged, and it stops current from flowing in that circuit. And if it can't flow through the capacitor, it can't flow through the resistor, and consequently that resistor is actually going to turn off. There is no current going in because the current in the wire everywhere is basically going to be zero. And also the voltage drop across that resistor is going to be zero at this point, because the voltage on the top plate of the capacitor is the same as the voltage on the bottom plate of the battery, so there's no voltage difference across that capacitor anymore, which goes along with the fact that the current is zero for that as well. So this light bulb would then turn off over time. You'd be really bright at the beginning, you'd be dimming, and then eventually this light bulb goes off when the capacitor gets charged. Another sample circuit, this time we've got our resistor and our capacitor in parallel with the battery. If you had this kind of circuit, when you first attach it in the immediate time interval, you imagine that capacitor like a closed wire. And so what's going to happen here is, this is one of those examples of electrons leave the battery, they have a choice of essentially going through a plain wire or going through a resistor, and that is the one scenario in which all of the electrons are going to choose the same option. All of the electrons are going to go onto the capacitor, and none of them are going to go through the resistor in that immediate time frame. It's essentially called a short circuit. It's a path back to the battery that avoids a resistor. So during this immediate time frame, there is no current going through the resistor, and that means that if it's a light bulb, for example, it's going to be off in that immediate time frame. Now, if we move to the a long time later time frame for this, that capacitor is going to charge up eventually and have the same voltage as the battery will. And at that point, current is prevented from going through the capacitor anymore. It's full, and there is still a complete circuit. There's still a loop for those electrons to get back to the battery, so they're all now going to start going through the resistor, so that resistor will light up in the long time later time interval. And you can again use Ohm's law to figure out what would be the power coming out of that resistor, assuming the same voltage as is existing across the capacitor. The last thing to talk about with capacitors is what happens when we discharge them. Okay, so we charge them up in that last step, and then what's going to happen if we discharge them? Well, first, usually have to do something to the circuit, change its configuration somehow to allow the capacitor to discharge, because the pressure from the battery basically pins those electrons and protons on the capacitor until it reaches its steady state voltage, and it's just going to stay there. It's just going to stay charged until I do something to allow those electrons to flow off, give them another path. One thing you could do is you can pull the battery out and just replace it with a plain wire. That would do it. or you can often change the path of that circuit with a switch somehow, like in the example below, right? So if we have this circuit, we've got kind of an interesting three-way switch there, or two-way switch connect to A or B. So if we wanted to charge the capacitor, we would connect the switch to A, and we're going to charge the capacitor until it has the same voltage as the battery, as shown in the example from the last slide. And then if we change the configuration of the switch so it's B, we've basically gotten rid of the battery in that circuit, so we're not pinning those electrons onto the capacitor anymore, and then current is going to flow off the capacitor around that circuit and back to the other end of the capacitor. In this case, you should realize the current is going to flow in the reverse of the direction that it was flowing when it charged, okay? Because obviously the positive plate is then going to, send current around to the negative plate. And if you were trying to calculate that current, or if you're trying to calculate the power dissipated, you would use whatever the fully charged voltage is from the capacitance as your power source, so as your V value for this circuit. Okay, so we've reached the end of this video. Hopefully you have a new understanding of a new device under your belt, and you can answer the essential question, which is how do capacitors act in a circuit with a battery and a resistor? Thanks for watching.